Hi, in this video, we are going to continue our course on problem solving for IOQM and RMO. From now on, we'll be looking at previous year's questions from RMOs and INMOs. So this is the first problem. This is RMO 2016 geometry. So let's look at it. It says, let ABC be a triangle and D is the midpoint of BC. Suppose the angle bisector of angle ADC is tangent to the circumcircle of triangle ABD at D. We have to prove that angle A is 90 degree. Okay, so let's draw a figure. Let's draw a triangle ABC. This is my A, this is B, this is C. And we have D is the midpoint of BC. So D is here. This is half and half. And you join AD and the angle bisector of this. So angle bisector will be somewhat like this. This angle is equal to this angle. Angle bisector of ADC is tangent to the circumcircle of triangle ABD. So we should draw the circumcircle of triangle ABD. So it will look somewhat like this. This is like a circumcircle of ABD, and this line is tangent to the circumcircle at the point D. Let's assume that this line meets the side AC at E, right? And let's also assume that the center of the circumcircle here is P. P is circumcenter of triangle ABD. Now our job is to prove that angle A is 90 degree. So since P is the circumcenter, if you join PD, that will be the radius. That will be the radius of the circle. And PD is the radius. Let's extend it and it meets this at F, let's say, this point F. This is a point on the side AB. Now we know that DE is tangent to the circle. Therefore, that implies that PD must be perpendicular to DE. The radius is perpendicular to the tangent. So this angle is 90 degree. So if I call angle ADC and angle ADE and EDC as X and X, I know that this much, which is angle FDA, is 90 minus X. Also, you can see by vertically opposite angle EDC is X, so therefore angle BD, and if you call that G, this angle is X. And obviously, because FDE or PD is perpendicular to DE, so PD is also perpendicular to DG. So therefore, this angle is also 90 minus X. So basically what we are getting is the line PD bisects the angle ADB. Since it also bisects the angle, since this is happening because we knew that DE bisects angle ADC. Because we knew that, we did some angle chasing, and because it was perpendicular to this side, PD was perpendicular to DE, we got that PD bisects angle ADB. Now, if PD bisects angle ADB, that means this line FD is an angle bisector. By the way, since P is the center of the circle, FD is also perpendicular bisector. Perpendicular bisector of AB. So what we know from there is that AF should be equal to FB, and we have FD is also common. And notice that these angles are equal. These angles are equal. So these triangles are going to be similar. Actually, they will be congruent because both the angles are equal and one side is also equal. So since they are congruent, what that means is that AD will be equal to BD. Because triangle AFD is congruent to BFD, right? Also, the incenter and the circumcenter of triangle ABD both lie on the same line FD, right? Because FD is angle bisector and because FD is also perpendicular bisector of AB, we can prove congruency of these two triangles. And therefore, AD is equal to BD. And we already know that BD is equal to DC because D was the midpoint. So now we have what? AD is equal to BD is equal to DC, which implies that the point D must be circumcenter. D is circumcenter of triangle ABC. Why is D circumcenter from triangle ABC? Because D is the point that is equidistant from all the three vertices. And now you notice that in the triangle ABC, the circumcenter lies on the midpoint of one of the sides. But that shows that this triangle ABC must be a right angle triangle and the right angle is angle A. Only for right angle triangles do you get that circumcenter is on the midpoint of the hypotenuse. So this finishes off the problem. It's a nice question which involves all the properties of triangles and some angle chasing. Let's move on. This was problem 101 from RMO 2016. Now we'll go to problem 102. This is also RMO 2016 problem. So the question says, let A, B, C, D, E, F be positive integers such that A by B is less than C by D is less than E by F. We are given, suppose AF minus BE is equal to -1. We have to show that D is greater than equal to B plus F. Okay. So let's analyze these conditions, these inequalities. So A, B, C, D, E, F are all positive integers, and we have A by B is less than C by D, which implies AD is less than BC. And since AD is less than BC, we can say AD plus lambda 1 will be equal to BC. Here lambda 1 belongs to positive integers, right? Since AD is a smaller integer than BC, you can add an integer lambda 1 to AD and you'll get BC. So this is our result 1. Similarly, from C by D is less than E by F, we can say CF is less than DE and CF plus lambda 2 is equal to DE. And lambda 2 is a positive integer. This is result 2. And then what we can see is we have AF minus BE is equal to -1. And we can rewrite it as AF plus 1 is equal to BE. And this is our result 3. Now what I will do is I will use these three results to try to prove this. So what I will do first is multiply it by F, the first equation, this equation by F. I will get ADF plus lambda 1 F is equal to BCF, right? Now AF here we have a term ADF. So AF in that can be written as BE minus 1. So I'll write D times. Instead of AF, I'll write it as BE minus 1 because AF is equal to BE minus 1 from 3. So BE minus 1 plus lambda 1 F is equal to, here I have a BCF. So BCF. So CF can be written as what? DE minus lambda 2, right? So B times DE minus lambda 2. How am I doing this? I'm writing CF as DE minus lambda 2 from this result. And I'm putting it there, right? So now notice what is happening. This expression is becoming DBE minus D plus lambda 1 F is equal to BDE minus B lambda 2. And BDE cancels with this DBE. And I end up getting basically lambda 1f, I'm getting lambda 1f plus lambda 2b is equal to d. Now we know that lambda 1 and lambda 2 are positive integers. So we know that lambda 1 and lambda 2 will be greater than equal to 1. So we can say that lambda 1f plus lambda 2b will be greater than equal to b plus f. If you replace both of them with 1, this must be bigger than this. So therefore d must be bigger than b plus f. And that is the proof of this problem. So an interesting question involving rational numbers and a little bit of manipulation. Let's move on. Question number 103. This is also RMO 2016 and it has two parts. We'll solve the first part in the beginning. It says, given any natural number n greater than equal to 3, prove that there exists a strictly increasing sequence of n positive integers in harmonic progression. So the first part of this problem is asking us to show that we can get a sequence of n strictly increasing integers, positive integers, which are in HP, right? So the way we will do it is we'll construct such a sequence. So it's a proof by construction. So we'll say let n greater than or equal to 3 be a given positive integer. First of all, we can construct a standard harmonic series. The standard harmonic series, the simplest one is 1, 1 by 2, 1 by 3, 1 by 4, till 1 by n. This is a harmonic series. If I multiply all the terms of this series by n factorial on all the terms, the resulting series is still a harmonic series. This series is still harmonic. N factorial by n, right? Because HP, what is the meaning of HP? It means that the reciprocal should be in AP. So if you look at these numbers, the reciprocals are in AP. The common difference is 1 by n factorial, right? So this is a harmonic sequence, but this harmonic sequence is a decreasing sequence. It is a decreasing sequence. However, I wanted to make a strictly increasing sequence of n positive integers, right? All of these are integers, by the way, right? So in order to get a strictly increasing sequence, I just have to reverse the order of this. So I'll just write it in reverse order. N factorial by n minus 1, n factorial by n minus 2, and finally it goes to n factorial by 2 and n factorial. This becomes a strictly increasing harmonic sequence of n integers, right? So part 1 has been done because we are able to construct such a sequence. Now we go to the slightly more complicated part 2, which says that prove that there cannot exist a strictly increasing infinite sequence. The earlier sequence was a finite sequence of n terms. Now we have to prove that there cannot exist a strictly increasing infinite sequence of positive integers which are in HP. So first part was proving that a finite sequence of positive integers can be increasing and in HP. And the second part is showing that it cannot happen in an infinite situation, right? So let's assume the opposite. We'll prove by contradiction. So we'll assume that there is an infinite sequence A1, A2, A3. This is infinite, strictly increasing strictly increasing sequence of positive integers. So all the integers here are positive, and this is an infinite sequence. What I will do, and we know that it is in HP. We have assumed the opposite, that there exists such a situation, such a sequence. Now what I'll do is define bk as 1 over ak for any k greater than equal to 1. Then what you can say is that b1, b2, b3, which are the reciprocals of this, will be a strictly decreasing infinite sequence of rational numbers of positive rationals which are in HP, which are in not in HP, they are in AP, arithmetic progression, because BKs are defined as the reciprocals, right? Now, what you will do is, let's say this is in AP, so the common difference of this D is going to be B2 minus B1, and since it is a decreasing sequence, it is decreasing because these were increasing, so the reciprocals will be decreasing. And since it is a decreasing sequence, D is equal to B2 minus B1 is less than 0, and that is the common difference. So that means automatically that B1 minus B2 is greater than 0. B1 minus B2 is a positive rational because all of these are rational numbers now. So let's choose an integer. Let us choose an integer n, which is greater than B1 by B1 minus B2. Notice this integer will be positive because B1s are all positive and B1 minus B2 is greater than 0. So B1 by B1 minus B2 is a positive number. And I'm choosing the integer higher than that. So it's the ceiling function for this. I'm choosing n as the integer higher than B1 by B1 minus B2, right? Now, we will take advantage of this and write the n plus 1th term of this AP. This is an infinite AP. So B of n plus 1 should be B1 plus n times D, right? And now let's think about what happens here. I will just write it here. B of n plus 1 is coming out to be, B of n plus 1 is coming out to be B1 plus the common difference was what? B2 minus B1. So B2 minus B1 times n. So think about it. This is equal to B1 minus B2 into n. And because B2 minus B1 was negative and this is now positive. And n is greater than what? B1 by B1 minus B2. So if you replace n with B1 by B1 minus B2, you will make this quantity smaller, right? Because you're subtracting by a greater thing. So what I can say is B of n plus 1 is less than B1 minus B2. And instead of n, we have written as B1 by B1 minus B2. Because n is greater than B1 by B1 minus B2. And from here we get this, and this is equal to 0 actually. B1 minus B1 is 0. So we are getting B of n plus 1 is less than 0. So what has happened is the n plus 1th term of this AP has become negative. But we knew that all the terms of this AP were positive because all the initial AIs were positive. So the reciprocals of positives will be positive. But now we have proved that the n plus 1th term is negative, which is a contradiction. Basically, we have achieved a contradiction, which means that such a series cannot exist. An infinitely increasing sequence of positive integers in HP does not exist. We have established a contradiction here. Let's move on to the next problem. This is problem 104, and this is from RMO 2014. This is an algebra question. We have to find all positive real numbers x, y, and z such that these equations are valid. 2x minus 2y plus 1 by z is equal to 1 by 2014. 2y minus 2z plus 1 by x is equal to 1 by 2014. And 2z minus 2x plus 1 by z y is equal to 1 by 2014. These equations have to be solved, and you have to find all real numbers, positive real numbers, which satisfy these equations. So obviously the first step here is add all of them. As soon as you add all three equations, you will end up getting this 1 by x plus 1 by y plus 1 by z is equal to 3 by 2014. This is the first result that we have. Another way to simplify these equations is to write them by taking z, the common denominator, and you get 2xz minus 2yz plus 1 is equal to z by 2014. And the second equation becomes 2xy minus 2xz plus 1 is equal to x by 2014. And the third equation becomes 2yz minus 2xy plus 1 is equal to y by 2014. And if you add these three versions of the equations, again, you will realize that these terms will get cancelled and you will end up with 3 is equal to x plus y plus z by 2014. And basically from there, we get x plus y plus z is equal to 2014 multiplied by 3. That is the second relation that we get. So a little bit of simplification converts these equations into these two versions. And now what I will do is multiply these two versions. If you multiply these two versions, what we get is 1 by x plus 1 by y plus 1 by z multiplied by x plus y plus z is equal to 9. 1 by x plus 1 by y plus 1 by z multiplied by x plus y plus z is equal to 9. And now since x and y and z are positive, we can apply a and gm on each of these brackets. We can say this is greater than equal to 3 times 1 by xyz to the power 1 by 3 times this is greater than equal to 3 times xyz to the power 1 by 3. So this gets cancelled, and we know that the left hand side LHS will be greater than equal to 9, applying AMGM twice. And the RHS is equal to 9, which means we have the equality case of AMGM. Equality case in AMGM inequality. And the equality case happens when all the three terms are equal. X must be Y must be Z, which guarantees now from these equations that all the three terms x is equal to y is equal to z is equal to 2014. That is the answer. So the answer for this will be 2014, 2014, 2014. We get it by basic algebra, simple algebra, and then applying AMGM inequality. Let's look at the final problem for today's session. This is problem 105. This is RMO 2015. Okay. So this problem says, let x, y, and z be real numbers such that x squared plus y squared plus z squared minus 2xyz is equal to 1. Prove that 1 plus x times 1 plus y times 1 plus z is less than equal to 4 plus 4xyz. This is what we have to prove. So let's rewrite the condition that is given here. We'll rewrite it as 1 plus 2xyz is equal to x square plus y square plus z square. And then do a little bit of manipulation here. Multiply both the sides by 3 by 2. You get 3 by 2 plus 3 by 2 into 2 becomes 3xyz is equal to 3 by 2 x square plus y square plus z square. And now we'll add 3 by 2 to it so that we can take common here. This becomes, both sides I'm adding 3 by 2. So it becomes 3 plus 3xyz is equal to 3 by 2 x square plus y square plus z square plus 3 by 2. Okay. Now this RHS, I will manipulate a little bit. I will write 3 plus 3xyz is equal to x square plus y square plus z square I have taken 1 of x square plus y square plus z square out, and half remains. I'll take that inside a bracket. So you would half x square plus y square plus z square plus 3, right? And this can be rewritten as x square plus y square plus z square plus half. This is x square plus 1 plus y square plus 1 plus z square plus 1. And this is equal to 3 plus 3 xyz, right? Now, we know some basic identities that x square plus y square plus z square is always greater than equal to xy plus yz plus zx. This is very easy to prove. You take everything to one side and you can express it as a sum of 3 squares, 3 perfect squares. So I can write this as greater than equal to xy plus yz plus zx. And inside here, I can write this as greater than equal to x square plus 1 is greater than 2x by AMGM. So 2x plus 2y plus 2z. This is greater than 2x, this is greater than 2y, this is greater than 2z. So what I get here is greater than equal to xy plus yz plus zx plus x plus y plus z, right? And on the other side, I have 3 plus 3 xyz. So I need to prove for 4 plus 4 xyz. So what I will do is I will add 1 plus xyz on this side, on both sides, right? So what happens if I do that? If I add 1 plus xyz on both the sides of the inequality, I get 4 plus 4xyz is greater than equal to, I'll write it here, 4 plus 4xyz is greater than equal to what? 1 plus xyz plus xy plus yz plus zx plus x plus y plus z. This is the right hand side now. I have added these two terms. And obviously you can see clearly that this is the factorization of 1 plus x into 1 plus y into 1 plus z, which means we have proved that 4 plus 4xyz is greater than equal to this. And that finishes off this inequality. I hope you understand what happened here in this particular question. We will continue with more problems from the previous year's questions, RMOs, INMO problems in the next few sessions. Till the exam, I'll continue making videos for this like these for you. And hopefully you will learn a lot from this. That's all for this one. I'll see you next time.